Greetings and welcome, friends. We're going to take a break from proving triangles congruent and talk about proving some things, some qualities within the triangles congruent. And today we're talking about the base angles theorem, the BAT. And it says this, that a triangle is isosceles when it has at least two congruent sides. True story. That's just definition of isosceles. When an isosceles triangle has exactly two congruent sides, exactly two, these two sides are the legs. All right, makes sense. Those are legs. The angle formed by the legs is the vertex angle. Wow, to be honest, I didn't even remember that. That's hardly ever referenced. But these other two, referenced far more often. The third side is the base of the isosceles triangle, and the two angles adjacent to the base are called the base angles. And today we are all about that base. Okay? That's what we're all about. And so the base angles theorem says this, that if two sides of a triangle are congruent, then the angles opposite of those two sides are also congruent. And then oddly enough, the converse of the base angles theorem, so this base angles theorem you can call BAT, and the base angles theorem converse, I'm fine if you just call it BAC, base angles converse. And that's, as you might predict, the converse statement, that if two angles of a triangle are congruent, then the sides opposite of those will also be congruent. So let us see if, first of all, I don't know, you probably believe this is true. Me and my buddies here, we did a Geometry Sketchpad kind of demonstration, which in reality, Geometry Sketchpad doesn't prove this. It's just kind of like showing me a good number of examples of it being true, where it seems to be true. But all it takes is a single counterexample to disprove something. So just because I can show you hundreds of cases in which it is true does not mean I've proven that it is. Question, comment? No, because I would need to prove that there doesn't exist some case in which I'm wrong. And unless I knew everything, I can't do that. No. I might be able to build an amount of confidence in you. Like I could show you a pattern about numbers and say like, all right, hey, check out these prime numbers. Here's a formula that works to give you the first 100 prime numbers. Therefore, I've proven a formula for all prime numbers. And it might work for the first 100. It could work for the first 1,000. But I would need some other way to show you that it actually will work for all of them. And that would be a hard thing to do. Those are Mersenne primes that I think you're describing, and 2 to the nth power minus 1 is I think the one that you're talking about. I believe. Yeah. But not all primes do fit in that pattern, but a good number of them can be predicted that way. And actually for decades, mathematicians believed that there was a particular prime number that was of the form of a Mersenne prime, and it took decades. I'd have to go back and check, maybe even hundreds of years before it was there. A counterexample was found, and sure enough, there was. The person was able to break it down into some factors, and with standing ovation. At a mathematical conference, just like, wow, you have disproved something that was believed for a long time. Well done, well done. So, all right, here for the base angles theorem, the BAT. Check this out. I like this. This orange line is not part of a triangle, but you can add, just like we added like a parallel line the other day to a sketch, you can add things to a sketch, and as long as it's legal and allowed, you're able to do it. And as long as it could be drawn for every isosceles triangle, then you're fine. So let's see. For given, I've got AB is congruent to AC is my gimme, right? Those are just like gimme points, just right? Like, here you go. Here's a coupon. You get a free point on the test. Oh, thanks. I'll take that, right? The givens are the best ones, right? So let's see. Then I could draw the angle bisector, all right? How about this? Draw an angle bisector of angle back, BAC. All right, and that's just like constructing an angle bisector is actually their reason. And I think you guys agree that whatever angle I give you, you could cut that angle in half, right? That's all I need you to believe right now, right? If you give me a 30-degree angle, tell you what, 15 degrees, just cut it in half, right? Even if it's an irrationally measured angle, it is possible to just take that and divide by 2. So this is possible no matter the isosceles triangle we're describing. Okay, now that I've done that, I could say that angle bad is congruent to angle CAD, computer-aided design. And why are those congruent? Well, by definition of angle bisector. Bisector. All right. And now where could I go? I think you guys might be able to take it away, Squidward. Count it down the sunset. Whoa, whoa. Let's not say things we can't take back. Where can I go from here? Well, for these two triangles that I'm looking at, this is what I'm thinking. Guys, where I'm trying to go, I'm trying to prove these two things are congruent. But notice I do conveniently have two triangles here, and I think I could prove these two triangles are congruent. So yeah, so AD is congruent to itself. And that's reflexive. Do I have enough information to prove the triangles are congruent? Yeah. I could say that triangle bad is congruent to triangle CAD. How do I prove that? Yeah, side angle side. Currently our only means of proving triangles congruent. And now here's some logic. I just showed that these two triangles are congruent. Our definition of congruent figures had previously said that that two figures are congruent if and only if all of their corresponding parts are congruent. That was a biconditional statement. It's true both ways. So I've just shown that these are congruent, and therefore all of their corresponding parts are going to be congruent. So that means I can actually say, because these two triangles are the same, these two things are congruent. Does that feel true? All right, so I can say angle B is congruent to angle C because, and I'm going to write this whole thing out, corresponding parts of congruent triangles are congruent. I think you could say definition of congruent figures there. Although we will eventually take this, we'll have a whole day for this concept. It's going to be abbreviated CPC, TC. Corresponding parts of congruent triangles are congruent. But yeah, it is definitely an application of kind of just definition of congruent figures. CPC, TC. Yeah. Now, I do want to point out, using CPCTC, you technically could also say that these two angles are congruent, and you could say that BD is going to be congruent to CD. All right, so there's a bunch more information that I could show, but I don't need to. I was just trying to prove the base angles theorem. And now, all your base are belong to us. Classic. Classic. All right, so let's put this to some easy use here. Where's my slider? All right, example 1. Name two congruent angles. And actually I could name them even briefer, but DFE, because there's only one angle at this vertex right now, I could just say angle F is congruent to angle E. But you're right, a three-point named angle is fine as well. And those are congruent by the base angles theorem, because those angles are opposite of the congruent sides. Right? Right. Here, how about this one? Ooh, I like this. I think I gave this to you. That's weird. It looks like it's... Oh, yeah, no, this is fine. All right, yeah, this is monitoring progress questions 1 and 2. Oh, whoop. So, it says copy and complete the statement. Already copied. Way ahead of you, friend. It says if HG is congruent to HK, so HG congruent to HK, what would be true? What would be true? Angle G is congruent to, I'm assuming you mean this. All right, I'll label it your way. GKH. I can't. There we go. GKH, right? And that's true by the base angles theorem. How about this one? If angle KHJ, so that's this angle here, is congruent to KJH, then what would be true? So if these two blue angles are congruent, yeah, KH is going to be congruent to KJ. And I'm labeling that with a double mark, but yeah. Congruent to KJ. And then since this is congruent to that, and that's congruent to that, it turns out that all three of these sides are congruent to one another by transitivity, which is pretty cool, I might say. Pretty cool. All right. Oh, wow. Check this out. Oh, I like this one. You guys are so gonna believe this. Geometricians love this theorem. All right. Corollary. If a triangle is equilateral, then it is equiangular, which they're arguing is a corollary to the base angles theorem. I think we're actually going to have you... I might have you prove one of these tonight. I don't remember which. But let's talk about how is this even related to the base angles theorem? Does anyone see the connection? Right, but check this out. Here's the logic. I'll give you a verbal rundown, Ryan, because I know you want it. Here we go. If these two sides are congruent, then by base angles theorem, these two angles are congruent, right? But I also know that, logic 2 here, I know that this side and this side are congruent. And then by base angles theorem, these two angles are congruent. And then by transitivity, I can show that all three angles are congruent to each other. Yeah, equiangular. It's a corollary because it's a short step from the base angles theorem, as I described there. So corollaries are still theorems in themselves. They're just kind of like, well, you didn't say a lot of new stuff there. It's like, imagine like you were working on some awesome thesis paper, and then like I came over and I was like, hey, you know what would be cool, Liam? Like, you should write your name on the top. And you're like, that's a great idea, Mr. Waddy. I'm like, I want some credit for that idea, though, Liam. Put my name next to it as well. And you're like, I kind of did more of the work here, and I don't think you really deserve all that much credit. You like, I was probably going to do that anyway, and like a corollary is just like a very short, small step, a simple idea tacked on to something that was a little bit more impressive, is essentially what it says. And then it turns out the corollary to the converse of the base angles theorem also applies. So that's the CCBAT. No. All right, let's put this to work. And I think you guys probably have believed this for much of your lives. I think you probably already assumed that these were true. So it says this: find the measures of P, Q, and R. Wait, they didn't tell me any measurements, guys. All right, corollary to the base angles theorem, they're all congruent. What else do I know? All right. So this is Corbat. Then by trisum, triangle sum theorem, try some potato chips. I know that measure of angle Q plus measure of angle P plus measure of angle R is equal to 180. By def of Kong, I also know that because these are all congruent, then their measures are equal. I guess I probably would have thrown that in here, but that's fine. So I could say measure of angle Q equals measure of angle P equals measure of angle R, because saying congruent is referring to the figure itself being the same size and shape. But now I'm talking about the numbers representing their size. So this is def of Kong. They weren't necessarily requiring all the explanation here. I just want to give it to you anyway. And if these are all equal, then by substitution, I could plug... well, I'll do it this way. If measure of Q is equal to measure of angle P, then I could plug measure of Q in for measure of angle P. And if measure of Q is equal to measure of angle R, then I could plug it in for measure of angle R. And I could have something to the effect of... And you guys probably logically had thought about this like 5 minutes ago already. But that's all right. Sometimes the ability to communicate it is more difficult. So here's substitution. And then combine like terms 3 times the measure of angle Q equals 180 degrees. Let's just simplify algebraically. And what do I do now? Oh yeah! The measure of angle Q is equal to 60 degrees as long as the others by transitivity. And why is that true? That's div prop equal. Div prop equal division property of equality. All right, we gotta get cruising here. All right, examples coming at your face. Bam, super fast. Look out! Can't dodge this. Example 3, speed of light. Bam. All right. Find the values of x and y in the diagram. Yeah. All right, someone tell me a statement they think is true. Y equals 4. And why is that true? Yeah, base angles converse or corollary of the base angles converse. Right, here's 2 angles that are congruent, therefore the sides opposite them are congruent, and then by def of Kong, yeah, y equals 4. Also, this triangle is going to be equilateral, so all 3 sides are congruent. And now what's a statement I could say? Yep. And why were these 2 congruent? Right? Yeah, because I had these 2 angles, therefore the sides opposite of them were congruent. And then I could solve that. I'd get x equals 3. So yeah, so I like that kind of problem. Yep. And then, spring is here, friends, and summer's coming soon. This is what you guys will all be thinking about when you're hanging out at the beach. You'll go ask that lifeguard, actually, next time you have a chance, and be like, how do you know these are isosceles? And he'll tell you. It'll be great. don't know. We'll see. All right, this one's actually a little bit intertwined a tad. It says in the lifeguard tower, PS is congruent to QR. So these are congruent. And QPS, so this entire angle, is congruent to PQR, this entire angle. Interesting. Explain how to prove that these two overlapping triangles are congruent. So I've got, this one's actually pretty hard to see. If I want to prove the triangles are congruent, I've got side, angle. Is there another side that I could find? Here's a side, here's an angle. For this to be an included angle, the other side that I'd need would be PQ. What can I say about PQ? Yeah, PQ is congruent to itself by a reflexive, right? And this is a little bit weird to see because these triangles are kind of overlapped in an irregular way, right? But notice I do have side angle side for that one, and side angle side for this one. So I could actually prove that those triangles are congruent. So triangle QPS is congruent to triangle PQR by side angle side. Sometimes it's not a bad idea to actually draw the blue and purple triangle like separate from each other, and just kind of like if seeing like the kind of the nested together is throwing you off. Sometimes breaking them apart can help you out. That's a terrible drawing, but not necessarily. And then it says, explain why PQT is isosceles. And that is regarding, let's see, PQT. So this triangle now let's see. Okay, they labeled this angle 1 and angle 2. If I had those two separate triangles, which now I guess I'll draw all over again, and if I could. All right, I've got that one, and I've got that one. Angle 1 is this angle, and angle 2 is this angle. I know these two triangles are congruent, and so I think I could say that angle 1 and angle 2 are congruent by corresponding parts of congruent triangles congruent. Right? Once I already knew that these big triangles were congruent, now I know that their corresponding angles will be. Because those are congruent, I can now prove that PT is congruent to QT. How do I know that? Yeah, converse of, the base angles theorem, which I just call back. And because two sides are congruent, then I could say triangle PQT is isosceles, is iso. By definition of iso, I guess, is good enough for me. All right, I want to have us get to some class question here, so I'm going to leave it from here. Goodbye, internet friends.